Hi, everybody. Anna is going to take over for the next 30 minutes or something to fill a gap. Then she's going to be back to tell us about spectral graph theory, which is what she's really here for. But Anna is a mega superhero because she's going to be solving these problems, well, with your all's help, on the fly, unprepared. Okay? Not easy, but she's going to do fantastic, obviously. And I will be back in less than 30 minutes.
Yeah, so while we wait for our super secret special guest, we have some extra time. So since Corey wantonly and gratuitously skipped so many lovely problems in here, let's see if we can figure out some of these induction problems together. I was here during Corey's lecture, but I didn't prepare this section. So hopefully you guys will help me if we get stuck.
Is the QED count going to be for you then? We can add it to your tally.
Yes, yeah. This is not Corey's.
Yeah.
So. And this is great. I needed to pad out my spectral QED count was not going to hit 31. So this will help. Okay, first problem apparently says that every fifth Fibonacci number is divisible by 5. Okay. Okay, so Fibonacci numbers. Let's remind ourselves what they are. So Fibonacci numbers are everybody's favorite recurrence relation. So they obey the relation Fn is Fn minus 1 plus Fn minus 2. And of course, if I tell you this relation, you need a couple of numbers to sort of seed into it to get started. So we're going to say here F1 is equal to F2 is equal to 1. If you started with different initial conditions, you would get different sequences. So we want to start with the right sort of base numbers here. Okay, so we're claiming that F5n is always divisible by 5, and we're supposed to do this by induction. So we're definitely going to need a base case, which I guess must be to find F5, and hopefully F5 is divisible by 5. So, okay. If you don't just have the first 5 Fibonacci's memorized, why would you not? But if you don't, how does it work to generate more of these? Okay, so for F3, I'll add together F1 and F2. So this is 1 plus 1 is 2. F4, I take F3, which is 2. I add 1, and I get 3. F5 is going to be 3 plus 2 equals 5. Okay, base case accomplished. Corey told me that there are efficient and inefficient ways to verify that the induction works. But so what would the inductive step look like? I'm going to fix n bigger than 1 and assume that f5 times n minus 1 is divisible by 5. I guess this is a nice thing to do after we had all that number theory. Hopefully you all remember what divisible by 5 means. And we want to somehow use this fact to show that f5n is divisible by 5. Okay, what is this screaming at us to do? The only way I know to get from f5n to something that I could apply my inductive hypothesis to would be to say f5n is f5n minus 1 plus f5n minus 2. And then apply the Fibonacci recurrence identity multiple times to lower these indices until we can get down to 5n minus 5. Okay, if somebody thinks that they see an efficient way to do this, tell me. Otherwise, I'm just going to start messing around. Yep, okay. Let me lower this first one first. So this is f5n minus 2 plus f5n minus 3 plus f5n minus 2. Okay. Now let me lower my 5n minus 2s. I have 2 copies of f5n minus 2 here. So 2f5n minus 2 plus f5n minus 3. This is 2 times 5n minus 3 plus f 5n minus 4 plus f 5n minus 3. Okay. So I have now 3 total copies of f5n minus 3. 2 copies of f5n minus 4. We're already pretty close to f5n minus 5. Okay, this is not as bad as I feared. Next, I mean, I don't know, I feel like continuing to just drop the bigger index seems like the right thing to do. So here I have 3 times f5 n minus 4 plus f5n minus 5. And then I have 2 f5n minus 4 left over. Oh, magical, happy day. Okay, everyone see what happens here? If I distribute this out, 3 f5n minus 4 plus 3 f5n minus 5 plus 2 f5n minus 4. Now, combining these two guys, I will get a coefficient of 5. So I have 5 copies of f5n minus 4 and 3 copies of f5n minus 5. And I'm going to write 5n minus 5 as 5 times n minus 1. So now, again, remembering induction from Corey's section a while back, how does this work? My inductive hypothesis says f5 times n minus 1 is divisible by 5. Let's remember back to when we were racking up those 31 QEDs in the number theory section. If I've got something that's divisible by 5 and I multiply it by something else, that's still a number that's divisible by 5. I don't have any inductive hypothesis that says anything about f5n minus 4, but magically, my coefficient here is a 5, which is divisible by 5. So I have one thing that's divisible by 5 because it's something divisible by 5 times another integer. I have another thing that's divisible by 5. We saw that the sum of two things divisible by 5 should still be divisible by 5. QED, 1. Okay, so I guess now we're just going to continue hunting through. We have several of these unselected things. Not doing that one. Yes, you can.
So it just so happens that F5 is 5.
Mm-hmm.
And I genuinely don't know, and if you don't know either, I wouldn't expect you to. Do we have another one that equals that number? Like F300, does that happen to equal 300?
Oh, that's a good question.
And then also, would that work for this? Like, could we find any, like, is F of that number going to ever be divisible by that number?
I think it's not going to be the case. Okay, I'm speculating heavily here. I'm trying to do this in my head. So for F6, F6 is strictly bigger than 6, right?
Yeah.
And then I think that you can convince yourself it will continue going that way. That for every Fn where n is bigger than 5, you're going to have a strictly larger Fibonacci number. Okay. Yeah, and the Fibonacci numbers, I mean, actually, they grow according to some exponential base, basically. So it's going to be much bigger than linear in general. In terms of other divisibility properties for Fibonacci numbers with certain indices, I don't know. I'm sure there are other nice facts about Fibonacci's.
Well, thank you. I know that doesn't do stuff.
Okay, so let's see. What's the next one that we're hunting for? Not that one, because I think it can be done by induction, but I think that there's a better non-inductive proof. So yeah, next. Yeah, let's do this. Another number theory flavored thing that we skipped. So it's
Yeah. You know, that's true.
Yeah, Anna, we've been looking forward to meeting you because we're all subsets of each other.
It is, yeah. I guess if you think of letters as commuting.
Yeah.
It is, for people watching the stream, my name is Anna, and we've got Nana and Hannah. So it's been crazy since I've been back. Like, half the time that anybody is mentioned, I feel like someone's calling my name. Okay, so fundamental theorem of arithmetic. Every integer n bigger than 1 should have a unique prime factorization. And we're going to try to prove this by induction. So, again, kind of doing it on the fly, but the great thing about induction is when you know you can prove something by induction, you can kind of follow your nose. So I'm trying to show something about every integer that's strictly bigger than 1. So my base case, what do we think? 2. That sounds like the smallest integer bigger than 1 I can think of. N equals 2. Does anybody know the prime factorization for 2? 2 has prime factorization 2. If you have a prime number, its prime factorization is just going to be itself. Hopefully we don't even need induction to convince ourselves that that's true in general. Okay, so not only does it have a prime factorization, it's a unique prime factorization. So my inductive step then I'm going to fix n bigger than 2 and assume all positive integers m with m is at least 2 and it's strictly less than n have a unique prime factorization. This is strong induction, I guess. I just have an inkling that probably I want to have this hold for everything that's smaller than n. And I want to show that this means that n also has a unique prime factorization. Okay, so I can think of 2 cases. One thing that could happen, which wouldn't really let me use induction, could be that n is prime. If n itself is a prime number, then we're done. I'm not going to somehow apply this hypothesis to conclude that there's a unique prime factorization. But I don't need to. As we said, every single prime should be its own unique prime factorization. So the work that I'm going to have to do by induction is on the composite case. So if I have a composite number, then I can write it as a factor of 2 things. I'm going to call them m and k, and they're both going to be strictly bigger than 1. So by induction, m and k have unique prime factorizations. I'm going to run out of letters. Qt to the beta t. Okay, they look like something like that. And so I can just jam these 2 together and get a prime factorization. A prime factorization of n. Now I probably need to do one more step to justify why this prime factorization should be the unique prime factorization of n. It is true, I say, okay, this is the only way I could decompose m, and this is the only way I can decompose k, but maybe you'd be worried, okay, what if I took two different composite factors? Could I somehow get different prime factorizations here? But I think we're going to be safe. Let me sort of just break this down into a separate thing. For uniqueness, I'm going to reuse letters here, which is not the best thing to do, but I didn't prep this, so perhaps you'll forgive me. Let's suppose for a contradiction that n has two different prime factorizations. Say p1 to the a1 through pk to the, or I don't want to use k, pl to the al, and q1 to the b1 through q c to the bc. Sometimes when you use so many letters, you just want to choose subscripts that don't make really logical sense as long as they're a distinct letter. Okay, so I want to convince you that these actually are the same prime factorization. And the way that I'm going to do that is use that nice lemma we have about what happens when a prime divides a product. So P1 divides, it certainly divides this product, right? I see I have a factor of P1 there. These two products are equal, so it has to divide this product. So it divides Q1 to the B1 through QC to the BC. And we know that anytime I have a prime that divides a product, it has to divide one of my factors. So this implies P1 divides one of Q1 to the B1 through QC to the BC. But really that means that P1 has to be equal to one of the QI, right? If I have a prime and it divides some prime to a power, the only way that that can work is if my prime actually divides Qi, and the only thing that divides Qi is itself and 1. Okay, so P1 equals some Qi. But now what can I do? P1 is a factor in here, and it's a factor in here. So I can divide both of these factorizations by P1. I'm running out of space a little bit. Sorry about the board work. Dividing both factorizations n over P1 has factorizations P1 to the A1 minus 1 through P L A to the L, and Q1 to the B1, Qi to the Bi minus 1 times QC to the BC. Now, by our inductive hypothesis, n over P1 is a strictly smaller number than n. So the prime factorization is unique. So these actually are the same. Not just the same number, but they're exactly the same prime factorization. They have, exactly the same number of distinct factors. Their powers are the same. They could be like relabeled and shuffled up, but they are secretly the same. And then to get the unique prime factorization of n, I just multiply P1 back into each of those. 2.
shortcut the first block of case 2 if you assume that m were a prime number? Is it reasonable or missing something?
No, that's probably true. Again, I thought about doing this, but I mean, I'm sure I've been in a class where this was done 5 years ago. But I've most recently thought about this about 5 minutes ago. So yes, I'm sure this is not the most efficient thing. As long as it's correct. Fibonacci numbers again. The nth Fibonacci number is less than or equal to 7/4 raised to the n. Da 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 da. Okay. So I want to show Fn is less than or equal to 7/4 to the n. I slightly suspect maybe this is one where I need multiple base cases. Let me just do a few to check.
Like all the things I've ever done with Nazi, like quite
Or 2?
Well, F1 is 1. That looks good. 1 is less than or equal to 7/4. F2 is 1, which is certainly less than or equal to 7/4 squared. Happily, 7/4 is bigger than 1, so when we raise it to bigger powers, it gets bigger, not smaller. Let's imagine that I can get away with 2. Usually, when you apply the Fibonacci recursion, you're going to get down to like Fn minus 2. So maybe I want to be able to break down more. Inductive step. Let's fix n at least 3 and try to check Fn. Okay, so Fn is Fn minus 1 plus Fn minus 2. So it's good that n is at least 3, so I can indeed apply my recursion. This is less than or equal to, by the inductive hypothesis, 7/4 to the n minus 1 plus 7/4 to the n minus 2. Okay, I think I see some algebra that I can do. I can factor out 7/4 to the n minus 2 to write this as 7/4 to the n minus 2 times 1 plus 7/4. So I'm done if this is less than or equal to 7/4 squared. 7/4 squared is 49/16. 1 is 4/4. I'm adding to 7/4. I get 11/4 or 44/16. And 49 is bigger than 44, at least on most days. 3.
class.
Okay, I think probably we'll just do one more. Let's try to find the Mantel's theorem.
Right here?
Yeah. It's probably stated slightly weird here. As an extra challenge to myself, I will try to use the notation that Corey used. I think that he wrote this way so that he didn't have to use floor functions. So this is, Corey said when he skipped this, he was like, it's my favorite theorem, but we're going to skip it. It's one of my favorite theorems too. So we had a graph theory section already. So we're going to go back to thinking about graphs. And a triangle-free graph, it's sort of what it sounds like. if I have a graph, a triangle is a set of 3 vertices that have all 3 possible edges between them. So it looks exactly like a triangle. And now we want to prove some fact about how many edges it's possible to have in a graph with 2 n vertices and no triangle. So I want to say that if a graph has 2 n vertices and n squared plus 1 edges, then it contains a triangle.
So that doesn't have a triangle.
This picture, yes, exactly, does not have a triangle in it.
There's a lot of triangles.
Even though it looks visually like you can see a lot of triangles, a triangle has to go between 3 actual vertices of your graph. So yes, this is a bipartite graph, so it has no odd cycles, and in particular, it has no triangles. It's, in fact, complete and balanced bipartite graph, which might be indicative to you of the number of edges that we're going for. Okay, so suppose G has 2 n vertices and n squared plus 1 edges. My goal is that G has a triangle. Base case, we're told that this works for n at least 2. So our base case will be n equals 2. So 2n is equal to 4. I have 4 vertices. Among 4 vertices, we're talking about simple graphs here. There's no loops, there's no multiple edges. How many edges can I have in total among 4 vertices? Like, what's the maximum possible number of edges I could see here? 6. Did you just hold up 7?
Oh, yeah.
I was so primed to hear the right. Oh my gosh.
7. Ruby doesn't work for 7, we get another QED.
Yeah.
Okay. The relevant thing here is that if n is 2, n squared plus 1 is equal to 5. Now, if I had all 6 possible edges, I definitely have triangles, right? If I have every single possible edge in my graph and at least 3 vertices, then any 3 vertices I want make a triangle. But the relevant thing here is that if I have 5 edges, then my graph just looks like this picture with 1 edge deleted. And any way you delete 1 edge, actually they're all symmetric. I still get a triangle left over. Actually, I'll get 2 triangles. Okay, so for 4 vertices, we can't put 5 edges in and be triangle free. Induction, we're going to fix n bigger than 2 and suppose Mantel's theorem holds for all smaller values. So this is another place where I'm going to want to have strong induction, really. Okay, the way that I know how to do this, I think that basically there's one inductive proof of Mantel's theorem. Consider a triangle-free n2n vertex graph. If it has no edges in it, it definitely has fewer than n squared plus 1 edges. So we can assume, I'll call this G. We may assume G has an edge. Here's my E. For concreteness, I'll name its vertices. And then there's the rest of G. I pull that edge and its vertices off. So I'm trying to use induction here. And let's think about why induction might be good. If there's no triangles anywhere in G, are there any triangles in this guy? No. So this is triangle free on 2 times n minus 1 vertices. So it has less than or equal to n minus 1 squared edges in sort of this part by induction.
Yeah, it's not strong induction in this case, right? Because it's
Oh, yes, oddly, because you require this to be an even number of vertices, it's not strong induction. You can prove this. Basically, the same theorem holds for odd numbers of vertices. There's a floor function, so it doesn't look quite as nice. But you can prove it by strong induction in general. You always take your graph and step down by 2. In this case, I guess it's just ordinary induction. OK, now we're actually almost done. Where else, if I'm trying to sort of estimate how many possible edges this graph can have, where else can it have edges? Well, I see one edge there. And if I have any other edges that don't just live in this cloud and are not just that edge, then they have to go across, right? So I could have an edge like that. Maybe I actually have many. But do I have a red marker anywhere? Yeah. Red is the universal color for bad things happening, right? I don't see that, right? If U and V have a common neighbor down here, then I make a triangle. Specifically because UV is an edge. So I had to choose an edge up there to start this. So note, UV have no common neighbor. So what's the biggest number? There's 2 times n minus 1 vertices down here. What's the biggest number of edges that U and V together can send down here? Yeah, 2 times n minus 1, or 2n minus 2 if you prefer. If they sent more than that, they would have to have a place where they both send to that vertex. Pigeonhole principle, yeah. So at most, 2 times n minus 1 edges between. Do we have faith that if I added 1 and that, I would get n squared? This is n squared minus 2n plus 1 edges here at most, plus 2n minus 2 plus 1. So I get minus 2 plus 1 all goes away. N squared minus 2n plus 2n. I can have at most exactly n squared edges if I'm triangle free by induction. So if I have n squared plus 1, there's a triangle somewhere. By the way, this picture is not just a random picture. This is actually the unique way that you could get exactly n squared edges in a triangle-free graph on 2n vertices. It's what we call a complete balanced bipartite graph. So I have n vertices on the top, n vertices on the bottom, and all possible edges between the two sets. And by the pigeonhole principle, you can see that there's no triangle in here. If there were a triangle, either it'd have 2 vertices on the bottom or 2 vertices up top. And just by like the multiplication principle, it has exactly n squared edges. Okay, so I think our special guests are ready. QED, yeah. 4, that's really going to be useful.
It's going to accumulate more.
Well, thank you very much. And I'll be back in half an hour or so for the actual things that I prepared to do.
Thank you, Anna. Awesome. Yeah, just